Welcome to HFCL Time Machine. Past, present, future, all connected.
Let's step into today's chapter where we explore how Wi-Fi 6 enabled uninterrupted connectivity for thousands of guests and what it means for the future of high-density event networking and large-scale digital experiences.
It's quite a topic, honestly.
It really is. Imagine a scenario for a second. An international pop star is on stage in a sprawling, rural Indian venue.
Right.
And in the crowd, a billionaire CEO pulls out their phone and hits upload on an uncompressed 4K video to their millions of followers.
Which takes massive bandwidth.
Exactly. And at that exact millisecond, almost 8,000 other high-profile guests attempt to do the exact same thing, live streaming, video calling, syncing massive files.
Yeah, and in a standard networking environment, the physics of radio frequency dictate that the network just instantly and catastrophically collapses.
Right. The access points get overwhelmed, the radio waves collide, and, well, everything just freezes.
Absolutely freezes.
Yet the world watched this massive, globally buzzed-about pre-wedding gala unfold in real time, completely flawlessly. So, welcome to the deep dive. Today, we are analyzing an exclusive case study from HFCL that proves the ultimate marker of modern luxury isn't the catering or the venue, it is the invisible digital infrastructure holding the entire experience together.
It is a phenomenal case study to unpack.
Yeah.
Because what we are essentially looking at is a masterclass in extreme radio frequency engineering.
And high-density network architecture, right?
Precisely. See, this was not a tech convention in Silicon Valley where you have a pre-wired grid and predictable traffic.
Right. The organizers were tasked with providing zero-latency, enterprise-grade connectivity for over 8,000 unique devices.
In a challenging, highly complex rural environment over 3 whole days.
Which is wild. So today we're going to look under the hood at the absolute micromechanics of how an indigenous Make in India deployment completely hijacked the laws of RF physics to make this happen.
And the stakes were monumental.
They really were. You see, the psychology of modern hospitality, especially for a demographic like this, global business tycoons, leading politicians, international dignitaries, has fundamentally shifted.
Absolutely. For this tier of user, seamless internet is no longer considered an amenity.
No, it is like oxygen.
Exactly, like oxygen. They do not want to see the routers. They do not care about the backhaul. They just expect infinite bandwidth the moment they unlock their screens.
Because they aren't just passive guests anymore, are they?
No, they are active, high-definition broadcasters. Every single attendee at an event of this caliber functions as a mobile broadcasting studio.
Right.
When you have this concentration of diverse, high-net-worth individuals converging, the expectation gap is the single biggest risk for the event organizers.
Because if the internet fails, the narrative shifts entirely.
Yes. It goes from the grandeur of the event to the failure of the infrastructure. The host family understood this foundational reality, basically. They knew that relying on legacy tech simply wasn't an option.
Okay, let us push back on that premise for a moment. Because I know you, the listener, might be thinking about your own home or office setup.
Right. The standard home Wi-Fi.
Yeah. I have a robust mesh network at home. It handles 4K streaming, countless smart devices, laptops compiling code, all simultaneously without dropping a single packet.
Sure.
So if an influential host family has essentially a bottomless budget, why is this an engineering challenge? Why can't they just procure 50 massive industrial-grade enterprise routers, scatter them around the venue, plug them into a fat fiber pipe, and call it a day?
See, it is a completely logical question, but it highlights a fundamental misunderstanding of how Wi-Fi actually operates at the physical layer.
How so?
Well, people tend to think of Wi-Fi like a lighting system. If you install a bright enough bulb, everyone in the room can see the light, meaning everyone has coverage.
That makes sense intuitively.
It does, but Wi-Fi is a half-duplex radio frequency medium. It is a two-way, highly contentious conversation.
So it's not just a broadcast.
Exactly. What makes 8,000 unique devices a nightmare isn't the square footage of the venue. It is the device density and the collision domains that density creates.
So it is less about the light bulb and more about thousands of people trying to talk into the exact same microphone at the exact same time.
That is a perfect analogy. We have to look at the underlying protocol, specifically CSMA.
Which stands for Carrier Sense Multiple Access with Collision Avoidance.
Right. In simple terms, before any device, your phone, your tablet, can transmit a single packet of data, it has to essentially listen to the airwaves.
Okay.
If it hears another device talking on that channel, it backs off, waits a random microsecond, and tries again.
Right. It is trying to avoid talking over someone else.
Yes, but when you put 8,000 devices in a concentrated area, that protocol completely breaks down.
Because everyone's trying to talk.
Exactly. The airwaves become so saturated that devices are constantly waiting, or worse, they transmit at the same time, causing a collision.
And what happens then?
When packets collide, they're destroyed. The router then has to ask the phone to retransmit the data. This creates a cascading snowball effect of interference, latency, and retransmissions.
Oh, wow.
So if you just throw 50 massive routers into a room like you suggested, you actually make the problem exponentially worse.
Wait, let me stop you right there. Why does adding more routers make it worse? Intuitively, more routers should mean more capacity, right?
You think so, but it's because of co-channel interference. See, there is a very limited number of clean, non-overlapping channels in the Wi-Fi spectrum.
Right.
If you have 50 routers blasting at maximum transmit power in a single venue, they inevitably end up broadcasting on the same channels.
So they're shouting over each other.
Yes. Your phone hears 3 different access points shouting on, say, channel 36, and it cannot decode the signal. The noise floor rises so high that the actual data signal is completely drowned out.
That sounds chaotic.
It is. It is the equivalent of putting 50 heavy metal bands in a single auditorium and telling the audience to just focus on the lead singer of one band.
That is a phenomenal way to visualize it. So just blasting signal everywhere is a recipe for a total network collapse.
Absolutely.
The RF environment becomes so noisy that the Wi-Fi essentially renders itself useless. Which I suppose brings us directly to how HFCL actually architected the solution.
Right, because they had to solve that exact physics problem.
Exactly. The host family bypassed the massive legacy international telecom providers and deliberately partnered with HFCL, leaning heavily into a homegrown Make in India initiative.
And, that business decision carries immense technical weight.
It does.
It is a statement that indigenous Indian engineering is capable of architecting at the very bleeding edge of high-density global networking. To solve the physics problem we just discussed, HFCL couldn't just guess where to place the hardware.
No, they had to be precise.
They began with an incredibly rigorous, exhaustive site survey.
Right, because we are talking about a highly complex physical environment. We have grand stages, massive dining pavilions, structural decor, perhaps heritage stone walls, and thick outdoor foliage.
Yes, all of it.
Every single one of these elements interacts with radio waves differently.
Absolutely. Think about the human body itself. Humans are essentially large bags of salt water.
Which sounds a bit morbid, but true.
It is. And salt water is exceptionally good at absorbing 5 gigahertz radio frequencies. When you map an empty venue, the RF propagation looks perfect.
But then the guests arrive.
Exactly. When you pack 8,000 people onto a lawn, the signal attenuation is massive.
Right.
The network engineers had to meticulously model the physical layout, factoring in structural attenuation, foliage interference, and the massive biological RF absorption of the crowd itself.
Which leads us to the deployment numbers. Based on that granular modeling, they deployed 204 Wi-Fi 6 outdoor access points.
Yes, 204.
Now, based on what you just said about po-channel interference and routers shouting over each other, I have to challenge this.
Go ahead.
You just told us that throwing 50 routers into a space creates a heavy metal echo chamber. How does cramming 204 access points into the venue not result in the exact same catastrophic interference?
That is the crucial pivot point of this entire engineering feat. The difference between a failed network and a flawless one is channel planning and power manipulation.
Power manipulation.
Yes. They didn't just turn on 204 access points and let them scream at maximum volume. They architected a microcell topology.
Microcell. Let us unpack how that works in this context.
Basically, instead of a few APs broadcasting over massive distances, they tuned the transmit power of those 204 APs way down.
Oh, they lowered the power.
Exactly. They essentially created 204 very small, tightly controlled bubbles of coverage.
Okay, I think I see where this is going.
By keeping the bubbles small, an AP on the north side of the dining pavilion physically cannot hear the AP on the south side.
Because the signal doesn't reach that far.
Right. And because they can't hear each other, the engineers can reuse the same Wi-Fi channels across the venue without them interfering.
I see. So instead of a massive floodlight blinding everyone, it is like 204 perfectly focused spotlights. The light doesn't bleed into the next circle.
Precisely. That is exactly it. And this is where the specific capabilities of Wi-Fi 6 really come into play.
Right, because Wi-Fi 6 was fundamentally designed from the ground up to solve the density problem.
It was. The case study specifically highlights the 2x2 MU-MIMO capabilities of the HFCL access points.
Multi-user, multiple input, multiple output.
Yes.
We know the acronym, and the classic analogy is usually the bartender, right?
Yes, the famous bartender analogy.
If legacy Wi-Fi is a single bartender serving one thirsty guest at a time, making everyone wait in a massive queue.
Which is terrible service.
Awful service. But MU-MIMO is like having a team of telepathic bartenders with multiple arms who can serve multiple drinks simultaneously.
That's a great way to picture it.
But for our audience, let's go a layer deeper. How is the AP physically achieving this simultaneous conversation?
See, it achieves it through spatial streams and phase manipulation. The access point has multiple antennas. In a 2x2 setup, it can transmit and receive two distinct spatial streams of data. Using advanced signal processing, the AP can actually alter the phase of the radio wave coming out of its antennas.
Wait, it changes the actual wave?
Yes.
Yeah.
This creates areas of constructive interference where the signal gets stronger, right where a specific client device is located.
Oh, wow.
And simultaneously, it creates destructive interference where the signal cancels out where another device is located.
So it is literally shaping the invisible radio wave in real time to beam data directly to a specific billionaire's phone, while simultaneously sending a completely different beam to the pop star's tablet on the exact same frequency at the exact same millisecond.
Yeah, exactly. It completely changes the math of network contention.
That's incredible.
But Wi-Fi 6 brings another crucial weapon to this density fight, and that's OFDMA.
Orthogonal frequency division, multiple access.
Yes. If MU-MIMO is about talking to multiple people at once, OFDMA is about the efficiency of the data packets themselves.
Let me try a mechanical analogy here just to make sure I'm following.
So go for it.
In older Wi-Fi standards, if my phone just needs to send a tiny text message, the router sends an entire massive delivery truck to pick up that one envelope.
Right.
The rest of the truck is completely empty, but it still takes up space on the highway. Other devices have to wait for that massive truck to clear the road before they can send their data.
That is a highly accurate representation of OFDM in Wi-Fi 5 and older. It is incredibly inefficient airtime utilization.
So with OFDMA and Wi-Fi 6, the router can essentially take that same delivery truck, slice the cargo bay into dozens of smaller compartments, and fulfill requests for 50 different devices in a single trip.
Exactly.
It puts a WhatsApp text in one compartment, a piece of a 4K video frame in another, a background app sync in a third, and delivers them all simultaneously.
Spot on. It slices the wireless channel into smaller subcarriers known as resource units.
Okay.
This drastically reduces latency for small, bursty traffic, which, as we know, makes up the vast majority of smartphone communication.
Right, all those little pings and background refreshes.
Yes. So when you combine the microcell power tuning, the MU-MIMO spatial streams, and the OFDMA packet efficiency, you begin to see how HFCL actually tamed the physics of 8,000 simultaneous users.
But, engineering the airwaves is only half the battle. You still have to manage the actual data flowing through the pipes.
Absolutely. The backhaul is just as important.
The case study heavily emphasizes quality of service, or QoS policies. And we know QoS isn't just a toggle switch in a settings menu. In an environment this critical, it requires highly sophisticated packet inspection.
Right. Because not all data is created equal. Think about the stakes.
Yeah.
You might have a major news outlet attempting a live broadcast from the event lawn.
Which has to be flawless.
Yes. While simultaneously 500 guests are passively letting their photo galleries sync to the cloud in the background. If you treat all those data packets equally, the background syncs will consume the bandwidth, and the live broadcast will stutter, buffer, and drop frames.
So how does the network instantly know the difference between a high-priority live broadcast and a low-priority photo backup?
Through rigorous tagging at the packet level, primarily using differentiated services code point, or DSCP tagging.
Okay. How does that work in practice?
Well, the HFCL deployment involved setting up specific SSIDs and writing complex rule sets at the network core. When a packet of data hits the access point, the system inspects its header.
Like checking a label on a package.
Exactly. If it identifies the packet as a latency-sensitive UDP stream, like a FaceTime call or live video feed, it tags it with a high-priority code.
So it is essentially a hyper-advanced post office sorting facility.
Yes, that's exactly what it is. The network physically queues the data based on those tags. The high-priority packets are pushed to the front of the line and placed in the VIP lanes of the bandwidth.
Ensuring they traverse the network with zero jitter and minimal latency.
Precisely. And the low-priority TCP packets like web browsing or background downloads are relegated to the remaining bandwidth.
Which makes sense. A web page taking half a second longer to load isn't a crisis.
Right. It ensures that the critical user-facing applications function flawlessly, even if the total capacity of the backhaul is temporarily saturated.
And what's fascinating is that the IT team wasn't just hoping these rules worked. They had real-time centralized management.
Oh, yes. Full visibility.
They could monitor the RF health, the packet drop rates, and the client roaming behavior across all 204 access points simultaneously.
Which allowed them to proactively mitigate bottlenecks before a single guest ever saw a loading icon.
Which brings us back to the core philosophy.
Mm-hmm.
The infrastructure must be invisible.
Invisible luxury.
The immense technical violence happening at the MX layer, the collisions being avoided, the packets being sorted, the beams being formed, is completely abstracted away from the end user. They just experience perfection.
And that's exactly how it should be.
All right, so we have thoroughly mapped the theory, the architecture, and the make in India hardware. But the true value of the HFCL case study is that they gave us the actual receipts.
Yes, the raw numbers.
We have the raw data usage statistics, and analyzing this data reveals the true brilliance of their network topology. Let us look at the sheer scale first.
The jump between the pre-event setup and the main event day is particularly revealing, I think.
It really is. According to the logs, during the pre-event phase, which, we can assume is the vendors, the setup crews, the logistics teams, the network had 73 access points online.
Right.
They logged 6,590 unique clients, pushing a total of 46.06 gigabytes of data. Now, 6,500 clients is already a massive load for any standard deployment.
It is a massive load. And 46 gigabytes implies heavy operational usage.
Like what?
Downloading massive CAD files for the stage design, coordinating logistics via VoIP, syncing production schedules, that sort of thing.
But then the tycoons and the A-listers arrive. The main event day hits. The network scales up to the full 204 access points.
With a full blanket.
Yeah. The unique client count jumps to 8,007, but the data consumption, the total data push violently spikes to 123.25 gigabytes in a single day.
Yeah, that ratio is vital to understand.
And it's crazy.
The client count only increased by roughly 20%, but the data volume nearly tripled.
Tripled?
Yes. This perfectly illustrates the shift in user behavior. The setup crews are consuming utilitarian data, but the VIP guests, they are consuming and generating massive, rich media.
Right. We are talking high bitrate streaming, continuous 4K uploads, and just massive bursts of social media traffic.
Exactly.
But here is where we hit the most fascinating anomaly in the entire case study. And I want to spend some time digging into this because it proves everything we just discussed about RF manipulation.
Oh, the frequency split.
Yes. When you look at the frequency distribution charts, there is a total behavioral flip. On February 8th, during the pre-event, 80% of the data usage was running on the older 2.4 gigahertz band, and only 20% was on the high-speed 5 gigahertz band.
Right, keep that 80-20 split in mind.
Right, but fast forward to the main event day, February 29th. The network geometry completely changes. The ratio doesn't just shift, it violently inverts.
It flips completely.
A staggering 95% of the massive 123.25 gigabyte payload is pushed exclusively over the 5 gigahertz band. Only a trivial 5% remains on 2.4.
Which is incredible to see.
How does an entire ecosystem of 8,000 independent devices spontaneously agree to abandon one frequency for another?
See, it is a brilliant display of forcing client behavior through network density.
Forcing them?
Yes. To understand this, we have to look at the roaming algorithms hard-coded into modern smartphone chipsets.
Okay.
You and I know the physical difference between the bands, right? 2.4 gigahertz has a longer wavelength, so it punches through walls, stone, and trees much better.
But it is slow and highly congested.
Exactly. 5 gigahertz is the multi-lane expressway, but its shorter wavelength means it attenuates, it dies off very quickly over distance or when it hits an obstacle.
So on February 8th, with only 73 access points spread across a massive rural venue, the 5 gigahertz signal simply couldn't reach everywhere.
Exactly. When a smartphone is deciding which band to connect to, it constantly measures the RSSI.
A receive signal strength indicator.
Right. If the 5 gigahertz signal drops below a certain threshold, say negative 75 dBm, the phone's baseband processor decides, this high-speed lane is too weak, I'm going to drop packets.
So it makes a choice.
Yes. To maintain a stable connection, the phone automatically falls back to the stronger, longer range 2.4 gigahertz band.
Oh, that makes sense.
Because the APs were sparse during setup, the worker's devices naturally gravitated to 2.4 gigahertz just to stay online amidst the sprawling stages and decor.
The phones chose reliability and range over raw speed. That entirely explains the 80%.
It does.
But then HFCL flips the switch on the main event.
Yes. They bring all 204 access points online. They activate that high-density microcell blanket we discussed earlier.
And what happened?
Suddenly, the venue is completely saturated with high-quality, low-noise 5 gigahertz signal. Everywhere a guest walks, their phone registers an incredibly strong 5 gigahertz RSSI.
So the phones no longer have a reason to fall back to the dirt road. The expressway is literally everywhere they step.
Precisely. And modern Wi-Fi 6 access points actively assist in this process using a feature called band steering.
Band steering.
Yes. When a dual-band device attempts to connect, the AP analyzes its capabilities. If it sees the device supports 5 gigahertz, the AP will actually ignore the device's requests on the 2.4 gigahertz spectrum.
Wait, it just ignores them?
Yes, effectively forcing the smartphone to connect to the faster, cleaner 5 gigahertz band.
That is incredible. They didn't just build a good network, they mathematically engineered the RF environment to manipulate the roaming logic of 8,000 distinct devices, forcing them to behave optimally.
Exactly. And think about it. If they had cheaped out, if they'd only deployed 120 APs, the 5 gigahertz blanket would have had holes in it.
And the moment there are holes, thousands of devices would hit that RSSI drop-off and cascade back down to 2.4 gigahertz.
Which would be disastrous, because 2.4 gigahertz only has 3 non-overlapping channels. It would have instantly buckled under the weight of those thousands of clients.
Right.
The fact that 95% of the data, which is 117.30 gigabytes, stayed locked onto 5 gigahertz, is the ultimate empirical proof that their 204 AP deployment strategy was flawlessly executed.
It really is a masterclass in capacity planning. And there is one final chart in the data summary that seals the argument, I think.
The AP usage distribution.
Yes, the AP usage category distribution for the main event day. It outlines how much data each individual access point processed.
Let's hear the numbers.
82.8% of the access points processed between 0 to 2 gigabytes of data. Only 9.3% processed 0 gigabyte, and a minute fraction handled the heavier loads of 2 to 5 gigabytes or 5 to 10 gigabytes.
Which is exactly what an RF engineer wants to see.
But let us play devil's advocate for a second.
Okay.
A CFO or a budget analyst might look at that pie chart and say, wait a minute, over 80% of our highly expensive enterprise-grade hardware barely broke a sweat. They only processed a gigabyte or two over the whole day. Did we drastically over-provision? Did we waste money on hardware we didn't use?
See, it is a common misconception, but in high-density networking, if your hardware is sweating, you have already failed.
Really?
Absolutely. What that 82.8% figure represents is perfect, symmetrical load balancing.
Explain the alternative. What does a poorly designed network look like on this chart?
Well, if you look at the analytics from a poorly planned festival or conference, you will see a massive disparity.
Like what?
You will see maybe 15 access points processing 40 to 50 gigabytes each, running at 100% CPU utilization, completely drowning in collisions and dropped packets.
While the rest do nothing.
Exactly. The APs on the perimeter are processing nothing. Those overloaded APs become catastrophic bottlenecks. The users connected to them experience massive latency, their battery life drains rapidly as their phones struggle to transmit, and the network essentially halts.
But because HFCL established that tight microcell architecture, the 123 gigabyte load was perfectly distributed.
Yes. 82.8% of the APs taking a small, highly manageable sip of the data means that no single radio interface, no single CPU, and no single backhaul switch was ever stressed.
They were just coasting.
Right. Every single piece of hardware was operating securely within its comfort zone. And when hardware operates in its comfort zone, the end user experiences zero latency.
There is no buffering.
There is no single point of failure. It is the definition of a highly available, fault-tolerant system.
When we dissect the raw data like this, the band steering, the microcells, the load distribution, it really contextualizes what the guests actually felt.
It does.
The report notes that attendees marveled at the connectivity, feeling as though they each had a dedicated personal router following them around.
Which is high praise.
They were completely insulated from the incredibly violent, chaotic reality of 8,000 devices screaming into the ether.
And that is the true triumph of this deployment. We started this deep dive talking about luxury.
Right.
True luxury is the absence of friction. The guests were entirely immersed in the grandeur of the celebration, effortlessly sharing their experiences with the global audience, completely unaware of the OFDMA slicing or the MU-MIMO phase shifts happening millions of times a second all around them.
If we pull back and look at the broader implications of this case study, it represents a massive paradigm shift, doesn't it?
It undeniably does.
Yeah.
On a global stage, with the entire world watching, this event proved that indigenous make-in-India technological infrastructure can not just compete, but can absolutely dominate in the most demanding, high-stakes environments imaginable.
Because historically, there's been a different assumption.
There has been an assumption that for elite, large-scale deployments, you had to rely on the legacy Western telecom behemoths.
Right.
HFCL dismantled that assumption by executing a flawless, physics-defying network architecture.
It redefines the blueprint entirely. It proves that we have the engineering talent, the hardware capabilities, and the architectural vision to power the most dense digital ecosystems on the planet.
Without a doubt.
As we look ahead to massive global summits, major international sporting events, and sprawling smart cities, this specific Wi-Fi 6 deployment methodology, the meticulous site surveying, the microcell power tuning, the aggressive QoS tagging will become the gold standard.
Absolutely. The demands on wireless spectrum are only going to increase. Devices are demanding more bandwidth, not less.
And the formats are getting heavier. AR, VR, 8K video.
Exactly. The strategies validated in this rural Indian setting are exactly what will be required to keep the hyper-connected world functioning seamlessly.
Which leaves us with a fascinating, slightly provocative thought to carry forward for you, the listener. For centuries, we have judged the caliber of hospitality by what we can see, taste, and touch.
The tangible things.
Yeah, the architecture, the floral design, the culinary mastery. But in our modern era, our experiences are fundamentally tied to our ability to digitally capture and broadcast them in real time.
That's very true.
If you have the most beautiful venue in the world, but the network drops your 4K stream, the experience is immediately degraded. So we have to ask ourselves, in the 21st century, is an invisible, perfectly balanced, impeccably engineered Wi-Fi network actually the single most critical element of hospitality?
I would say yes. If it's done right, nobody will ever thank you for it. But if it fails, it is the only thing they will remember.
A profound reality for the digital age. Next time you're at a packed venue surrounded by thousands of people and your message sends without a second of hesitation, take a moment to appreciate the immense, invisible war being waged against physics to make that simple convenience possible. And that brings us to the end of this chapter in the HFCL Time Machine. Until next time, stay connected to what's next.
You've been listening to HFCL Time Machine. For more conversations like this, find us on LinkedIn, Instagram, and YouTube.